We don't.
Okay.
Oh,
Does it work now for people on Zoom?
Yeah, it can hear because.
Okay. I guess this says it works, so let me just double check. Yes, okay, thank you. How do I get rid of this? Okay. Yeah, so I was saying like, okay, so this, okay, okay. Okay, I was saying the quantum entanglement receives a lot of attention because it plays a central role in the field of quantum computation and quantum information science. And as simple examples, a lot of the fundamental routines or procedures in fault-tolerant quantum computation relies on creating quantum entanglement between different qubits. So for example, here I get this figure from Wikipedia. So in the example of shellcode, you could encode information on one logical qubit into a highly entangled state of 9 qubits. Now, for physicists' point of view, quantum entanglement is also very useful. You could use it to extract useful, important physical properties of your quantum system. So for example, I think. Okay, now it works. So for example, by inspecting the scaling behavior of quantum entanglement with respect to, say, the size of your subsystem, you could use it to detect quantum phase transition. Or if you're interested in some auto-equilibrium process and you want to extract some physical dynamical properties, you could study the time evolution of quantum entanglement in such processes. Or, as famously well known, that quantum entanglement can also be used to detect topological order in the context of topological entanglement entropy. So it's a very useful subject, and both for quantum info people and physics community. The second subject that my talk will touch upon concerns symmetries. So maybe starting from the birth of physics, or maybe like at least a very, very long time ago, people already know symmetries are very useful. For example, it provides important guiding principles for model building, and it can be used to constrain dynamics of quantum systems. For example, global symmetries and the associated Duft anomaly can be used to constrain the possible infrared phases of your physical system. And of course, it plays a central role in the classification of quantum phases of matter. Now, there's also considerable lots of recent developments regarding symmetries, so I'll give you only 2 examples here. So a lot of the past considerations for symmetries concerns closed quantum systems. So now there's a lot of efforts to generalize these kind of efforts to open quantum systems or symmetries in mixed state quantum matter, where a lot of you here are experts, where you distinguish, say, the notion of strong and weak symmetries, depending on whether you allow like a charge exchange between your system and the environment. Another direction which is very interesting, and also like attracted energy theorists, condensed matters people, and the pure mathematician, is the notion of generalized symmetries. And as I know, Sarah very kindly like scheduled the seminar as part of this generalized symmetry journal club. So I hope I'll say something about generalized symmetries during my talk whenever I get a chance. So it's like the generalized symmetry is like a notion to generalize the definition of symmetries to include broader phenomena. So examples include higher form symmetry, higher group symmetry, non-invertible symmetries, and subsystem symmetries. And again, now like there are lots of efforts to carrying over what you know from the ordinary symmetry, and then say what actual interesting structure you get for the generalized symmetries. Now, the third subject that my talk will touch upon concern defects in quantum systems. Now, of course, defects such as quantum impurities, which are point-like, or domain walls separating different order regions, are important if you want to describe, say, natural phenomena, because they're often there to include in your model building process. Now, why do I care about defects? So as a theorist or from a theoretical point of view, the defect problems gives you a natural playground to explore various analytical methods to model these defects both in lattice systems and continued effective field theory. So there's a huge amount of efforts right now in both in the lattice community and the continued field theory community to study interesting problems concerning defects. And secondly, recently there's also more experimental efforts, which I can't say I'm not really an experimentalist, but I've been reading something related to this. So there are lots of efforts on experimental engineering of defects in spectral systems for quantum information science purposes, for the potential of the defects in, like, say, quantum information storage and processing. And then last but not least, for simulation communities, these kind of defects problems in strongly interacting systems are also very natural candidates for both classical and quantum simulation. Okay, so I told you that today I'm going to tell you some stories between these three subjects. Let me also say something about the physical setup I would like to use to study these three things, namely out-of-equilibrium processes. So such as, for example, quantum quench or periodic drive. In the case of quantum quench, what you do is, for example, you prepare states, which is, say, a ground state or some low-lying excited states of some Hamiltonian H1. And then at t equals 0, you switch on a different Hamiltonian, such that your state is not an energy eigenstate of the new Hamiltonian anymore. As a result, your physical observable will have time dependence until your system relaxes again, such that your observables relaxes to some stationary value. From the short time dependence of your observable, you could try to extract information such as the excited state spectrum of the new Hamiltonian. And if you look at the long time limit, that could tell you something about some normalization properties of your system. Now, the periodic drive is sort of like a more extreme quench, like in the sense that you're somehow like switching between two Hamiltonians, so like you're constantly quenching between two Hamiltonians. And here there's no energy conservation. So generically speaking, as I will say some words about exceptions later, generically speaking, your system will heat up to infinite temperature at relatively short time scales. So now, why do we care about this kind of processes? Why do we want time dependence? First of all, lots of processes in nature are not in equilibrium. So like if you want to try to study these things, then you should care about this kind of theoretical modeling problems. So there are lots of theoretical interests, for example, summarization or pre-summarization, dynamical quantum phase transition. And also I should say that in this kind of non-equilibrium processes, you could be able to discover new quantum phases of matter, such as this kind of Floquet topological phases. And again, also their recent experimental advancements gives you actual engineering control power of these processes, which also motivates theorists to think more about these problems. And then again, last but not least, quantum simulation communities, this kind of outer equilibrium processes is also favorable because, for example, here in this periodic drive case, you could translate this kind of setup conveniently to something called Floquet circuits, and then put it implementing either digital or analog quantum simulation setup. And then you could try to study various things. So there being lots of work recently to try to consider this kind of processes in the quantum simulation setup. Okay, so that's the motivation part. Okay, so it took shorter than I thought, but please stop me at any moment if you have any comments or questions or anything you would like to say. So that's the motivation. Before I go into details, I will tell you some, just overview what I'm going to tell you today. Today, my talk will be divided to two parts, not necessarily equal time. So like maybe there are different ways. I don't know at the moment, perhaps a little more in part one. Okay, so part one of my talk will be focusing on the intersection of quantum entanglement and symmetries. In particular, this is under the notion of so-called symmetry-resolved entanglement, which in a one-sentence summary, it gives you a refined structure of quantum entanglement for quantum systems with a global symmetry. And there's been maybe hundreds of papers on this. I didn't count, I think maybe 300 of papers in the last 4 or 5 years. So you could ask, like, what am I talking to you here today? Like, what could I possibly tell you? Like anything new or anything interesting? Okay, this might not be interesting, but this is what I'm going to tell you today. Namely, this talk, again, I'm going to focus on the outer equilibrium processes. So here, I will briefly tell you something like a computational framework, which is suitable for tracking the dynamical evolution of symmetry-resolved entanglement and the associated question of the probability distribution of the amount of symmetry charge contained within a subsystem, which I will tell you in more detail later. this kind of quantities in symmetry-preserving out-of-equilibrium processes. So this is based on some preprint we put on arXiv last December with my fantastic collaborator, Sarah Murciano, who was at Caltech when she just accepted a permanent position at Secley, and Pasquale Calabresi and Robert Koenig, who is at BNL. So that's part one of my talk. In part two, I will switch gears, but talk about the intersections between these two subjects, symmetries and defects, in the context of so-called topological defects. So as I said, topological defects have been studied both on the lattice and the continuum in many different dimensions. I guess not that many different dimensions, but 1 plus 1, 2 plus 1, 3 plus 1. Today, I'm just going to tell you some story about 1 plus 1D on the lattice. In this context, topological defects can be viewed as some sort of local modification to your Hamiltonian, such that your physical observables depend very mildly on the defect location. And generally, you could move the defect around. As long as it doesn't cross over some other operator insertions, your physical observables or correlation functions would not change. Now, again, this subject is like maybe 1,000 paper, that's an overestimate. So what I'm going to tell you today is some perspective, which I think is much less investigated in this field, namely the roles played by topological defects in constructing long-lived physical quantities. So this kind of topic has various connections with different fields, such as non-invertible symmetries or crystallization, Floquet circuits. And I will only tell you a small part of this work with Robert Koenig and Aditi Mishra from NYU, which is another paper came out last October. Okay, so I'll start with part one of my talk. Are there any questions or comments at this moment? Okay, I think I'm keeping track of chat. Okay. Okay, so part one. So before I tell you about symmetry resolution or quantum entanglement, I would like to remind ourselves the basic definition and properties of quantum entanglement in quantum many-body systems. And throughout my talk, I will only be focusing on so-called bipartite quantum entanglement, although I'm happy to chat more about multipartite case. Okay, so suppose you have a quantum system and you just divide your space into two parts called A and A complement. So it has a spatial bipartition, and your total system is in a pure state. So think about your system is like a closed system, and you have a pure state on the total system. Now, the important thing that I want to say right now is I make the assumption, right? The total Hilbert space is a tensor product of the Hilbert space associated with A and the Hilbert space associated with A complement. So this would be a natural setup, for example, when you consider spin chains where your physical degree of freedom lives on the sides. Now, of course, this assumption does not work in general. So for example, for lattice gauge theories, where you have physical degree of freedom both on the sides and on the links, you need to be very careful about where you cut the subsystem. And there are various things you need to consider. And not to mention, if I'm in the continuum, in the language of continuum field theory, you can't just literally cut open things like that. You need to put in some regularization stuff at the entanglement cut. And I will not talk about those things at all today, because that's going to mask the message I want to convey today, but I'm happy to chat more after the talk. So make this assumption. And then a natural question you could ask is, I have a pure state. Can I write this pure state as a product state, namely some state sets up A taken from the Hilbert space on subsystem A, and another state sets up A complement taken out the Hilbert space on the complement. So of course, generically, this kind of situation might be special, but if it does factorize, then when you compute correlation functions of observables restricted to A and with observables restricted to A complement, then this whole correlation function will factorize. So in the other sense, there's no quantum correlation between the two parts of the system. On the other hand, if a pure state that cannot be written in this manner implies there's quantum entanglement between A and A complement. So is there some method to detect this kind of bipartite entanglement? There is, and this is a thing called von Neumann entropy. So what to do is you could trace out the degree of freedom on A complement and obtain the reduced density matrix. The reduced density matrix is a Hermitian operator acting on A, with non-negative eigenvalues, where the sum of those eigenvalues is equal to 1. So then the phenomenon entropy is defined by minus trace over A, rho sub A, log of rho sub A, which you could also interpret as correspond to the classical Shannon entropy if you interpreted those non-negative eigenvalues as entries of a probability distribution. Now, I said that the total system is in a pure state, and that's my assumption for the whole talk. So in this case, phenomenon entropy does detect quantum entanglement between A and its complement. However, in general, if your system is in a mixed state, then phenomenon entropy cannot reliably detect the actual quantum entanglement between A and A complement. You need other methods like logarithmic activity or conditional entropy. And that's not what I'm going to talk about today. Another thing is one could ask, how do you actually compute phenomenon entropy? So you say there's a log inside the trace. Of course, if you could diagonalize the density matrix, there's no problem. You just substitute it in. But what if you couldn't in general? So one trick is the so-called replica trick, which let you get around this kind of like complicity by considering the so-called Renyi entropy, which is defined as following. So in particular, you say the log is now outside the trace. In particular, you would just be computing trace of nth power your density matrix, which you don't have to diagonalize your density matrix anymore. And taking the angles to one limit would supposed to recover for you the phenomenon entropy. However, this limit is simpler to just say take the limit than actually being done, because to actually be able to take this limit, you need to be able to write the Renyi entropy as an analytical function of n, which is very rarely possible in general. Now I introduce a Renyi entropy as if it's some sort of like a complement product or computational intermediate tool to get to you the phenomenon entropy. However, Renyi entropy has its own meaning for like particular values of n. For example, n equals 2 is also what people, it's related to something called purity, which you could use to detect whether your density matrix is literally a projector or not. And also, one can measure these Renyi entropies in experiments. So for example, if you want to measure second Renyi entropy, you would create two identical systems and then make some quantum switch. And then by taking the overlap of the ground state wave function between different configurations, you could extract second Renyi entropy. And I should say, like by experimentally acceptable, I meant by experiments maybe 5 or 6 years ago, because now we have a more powerful technique called the classical shadow tomography, which is more powerful for getting this kind of entanglement methods. Okay, so as I said at the beginning, the phenomenon entropy, which detect bipartite entanglement, can be used in various physical purposes, and which lots of people have studied this before. Now you could ask a following question. Suppose I have more constraints in a quantum system. Suppose your quantum system has some global symmetry. Is there a refined structure of quantum entanglement? And that brings us to the topic of the so-called symmetry-resolved entanglement. So again, this subject, it started to like boom maybe from 2017 or 2018, and there are now hundreds of papers on it. But what's fascinating to me, because I was a mathematical physicist or string theorist, so what's fascinating to me is like a lot of the effort in this field is motivated by an experiment. So which is what I'll tell you next. So in particular, this experiment was done by these people where many of them were in Boston back then. So this is a paper in, I think, 2018 or 17. I don't want to bet on which one. But they studied, in particular, entanglement properties of a many-body localized system with particle number symmetry. So in particular, they take some system where the total particle number is fixed, and then you just divide it by two halves, A and A complement, or B. This is taken from this paper. Okay, so now what they do is to track. So I'll tell you what they do later. But the key idea of this paper is that there's some refined structure of the total quantum entanglement. In particular, it could be split into two parts: the so-called number entanglement and configurational entanglement. Where number entanglement you could think of as stems from states, superpositions of states with different particle numbers in your subsystem A. So for example, there are 4. If you totally have 8 particles, you could have 4 in subsystem A, or you have 3, or you have 2. This kind of particle number fluctuation with your subsystem generates a number entanglement. or said otherwise, it's generated by particle transport across the boundary of your subsystem. However, there's another part of the entanglement, which is what they call configurational entanglement. This comes from superpositional states where the particle number in your subsystem A is fixed, but they have different configurations. So in other way, the configurational entanglement you could view as being generated by particle interactions and particle motion within the subsystem. The key thing that they observed in this experiment is that there are different time scales of this entanglement dynamics with respect to number and configurational entanglement. In particular, in a typical quench setup, the number entanglement will grow linearly and saturate very quickly to some stationary value, which obeys area law, but in 1+1, the area law just means constant. On the other hand, if you look at configurational entanglement, it has a much slower growth, a logarithmic growth, where it saturates to some value, which has a volume mode dependence. So in particular, theorists were thinking why do these two types of entanglement has different growth behavior, and in particular, how do I think about this kind of refined structural entanglement? As you could already notice here, if I want to quantitatively study configurational entanglement, I will need to fix a condition where my subsystem A really just has 4 particles, or it has a U1 charge Q equals to 4. So I need to imply this extra constraint to think of quantum entanglement, even the simplest bipartite entanglement case. So that's what motivated people to study these kind of topics, both in lattice systems and conformal field theories. And I just gave you here a completely incomplete list of all the references, so there are many, many more. In the following, I will just try to more rigorously define what is symmetry-resolved entanglement, and before telling you some of my own work in this regard. Okay, so what's a general setup? I think, okay. So suppose, okay, I should say that today I'm just in 1+1D, so everything's 1+1D. There could be generalizations in higher dimensions, but that's not what my talk will focus today. So we're in 1+1D, you consider a quantum system with a bipartition with some global symmetry G. Now for today's purpose, I'll just be U1, so for example, number symmetry example in the previous slide. So now my total system is in some pure state with a particular U1 charge, capitalized Q. And then you could trace out the complement to get reduced density matrix. One thing you immediately ask yourself is, even though the total system has a fixed U1 charge, the U1 charge containing the subsystem A is not fixed. It could be 1, 15, 100. So in general, it's there's some probability that you find a particular charge on the subsystem. So consequently, you could show that your reduced density matrix could be written as this sort of block diagonal form, where each block corresponds to a particular U1 charge confined to the subsystem. So like charge 1, 5, 15, da, da, da. Now, if you want to quantitatively quantify how much entanglement is contained, for example, in this particular block, a very natural thing to do is I just take out this block, right? I just forget about everything else, just take this block out. And mathematically, that just corresponds to apply a projecting operator to this particular charge sector, compose it with the original density matrix. However, we're not quite there yet. This is not literally a density matrix because we call density matrix and need to have trace equal to 1. So you need to normalize a trace in this way. And in this way, this gives you an effective density matrix for this particular subsystem charge sector. Now, I will say a few more words about this normalization factor because it's it has a physical meaning. Because if you just look at it, the trace over A, rho sub A composite pi sub Q, this tells you the probability of finding charge Q in your subsystem A. So in general, this is a probability distribution, and I will say more about that later. Okay, once you have this effective reduced density matrix, you could just copy paste like what you had, like the ordinary entanglement methods that you had before. You can copy paste them. So you could define symmetry-resolved range entropy and symmetry-resolved phenomena entropy just as before, except you just replace your original density matrix with this effective density matrix. And there are lots of interesting properties of this kind of symmetry resolution. In particular, you could ask what's the dependence on the charge or the representation, what's the scaling behavior. So I will not say like maybe I should have given you like some summary of that property, but I think given the time, I could say more if you ask me during talk or after talk. Okay, so now comes to my point is what I did in this field, which is concerns the time evolution of this sort of like symmetry resolved entanglement that I just introduced to you before. So in general, it's very difficult to study time evolution of entanglement analytically. You could always do numerics. I should say that for integrable systems, there's an effective theory in terms of quasi-particles, which gives you quite a bit of mileage to analytically study this kind of time evolution of entanglement problems. But in general, it's very difficult. However, we could still ask ourselves, what does it take if I want to analytically track this kind of time evolution? The logic is actually very simple. So suppose you pick a basis for your Hilbert space of your total system. I'll call it set up I. Now, if your outer equilibrium process is symmetry preserving, and in particular, you started with some particular symmetry charge, this I just basis for this subspace correspond to the charge. Now, at any given time, you just write your state in terms of linear combination of this basis. So your time dependence is transferred to this coefficient. Now, I could write down the time-dependent reduced density matrix just per definition. And if you do that, you realize that it's given by a linear combination of this sort of like generalized reduced density matrix, namely the same like in this right rectangle, where your in state or cat state and the out state and or broad state are in general distinct from each other. So it's just some messy thing. And then it's clear that if I want to compute any entanglement methods built out of those rho sub A, and using this basis, I would have to take into account our cross-term contributions, where the in state and out states are distinct from each other. And this setup was considered by my collaborators in the concept of Renyi entropies. And what we did in this paper last December was to generalize this framework to include to track the time evolution of symmetry resolved entropies. So in particular, we introduced a notion of symmetry resolved generalized Renyi entropy, which in a sense, it's very similar to the ordinary symmetry resolved Renyi entropy, except that now at each copy of the replica, those psi sub 1, psi sub 2 to psi sub 2n, they could all be different states. So you get this whole mess, like originally the size are all equal to some particular total system state. Now they could be all different. They take values in this basis that you choose. So how do you compute this thing? As what we normally do in physics, we could go to Fourier space. What does that mean is you could write this projector and, for example, into charge Q sector explicitly. See the following form. So you just write it as an integral over your group element. And in particular, this involves insertion of a actual operator e to the I theta Q sub A, where Q sub A measures the charge contained within your subsystem A. So then, if you substitute into here, that leads you to define this quantity with fundamental building block of this generalized entropy, namely the generalized charge, which looks like you're taking the trace over nth copies of the reduced density matrix, except for two differences. First one, of course, like each in or out states or broad cat states in each replica copy could be all different. And additionally, you have the actual insertion of a fugacity term, which you could view as turn on some U1 flux coupled to this charge operator, which measures the charge contained within the subsystem. Okay, so this looks like, okay, something simple, but in general, it's very difficult to compute this. But in conformal field theories, you could actually use the power of conformal transformation to translate computation of this quantity to some partition function here, in this case, on the cylinder, with the insertion of a U1 symmetry defect. So it's like some sort of twisted partition function, but with like all these 2n extra fields insertions around the mirror ring of the cylinder. So for generic CFTs, it's still very difficult to compute. What we did in this paper was to consider like a special CFT free compact boson, which also is very relevant to anything involving Luttinger liquids. So it has practical applications where we were able to find some analytical formulas for this kind of calculations, at least at the leading order. And we also could benchmark with lattice simulations and things like that.
Can I ask about
So
you made the comment that you are intending to think about this as an entanglement measure. So are you able to verify that Clearly it's not negative, but is it invariant under?
Yeah, maybe I should say, I could say, so there is some quantitative say, you could say, I didn't make this comment, namely, here I said in this experiment, I had this total entanglement split into these two. So you could write your total phenomenon entropy as the sum of these two. This number entanglement is like the Shannon entropy for this probability distribution, which I will talk about later. This configurational entropy is like a weighted sum of the symmetry resolved and entanglement entropy that I introduced. So quantitatively, you could write this kind of equality. But on the other hand, if you just restrict to a particular symmetry charge sector, I think, as I said earlier, there are lots of nice quantities you would imagine for total entanglement. I don't know how to prove them or something.
So it's not been demonstrated to be.
No. Okay, so I'm not claiming that it's an entanglement method, but it's more like a refined structure of your total entanglement in the sense that you could write it as these two parts. And and these two parts have different like physical properties. They grow differently in some sense. Yeah, maybe there is like, I'm interested to think more about them as actual entanglement methods, but yeah, it's not being yeah. Thanks. So okay, so going back to this charge moment. So here again, like I introduced this quantity just out of the blue, like I just write a projector in this way. Okay, that, and then but this quantity also has its own physical meaning. In particular, if I take n equals 1, this gives you the generating function to study this kind of probability distribution that I mentioned earlier, which is what I'm going to say next. So let's first start again with the equilibrium setting. So I'm in my total system in some state with a fixed U1 charge. And then I could trace out the complement to get the reduced density matrix. As we said earlier, fixing the total system charge does not fix for you the charge contained in the subsystem. So you could ask, what is the probability that the subsystem A contains U1 charge, say 100? So you could compute this exactly by this normalization factor that I mentioned earlier. So trace over A, rho sub A composes this projector. Now going into Fourier space, the generating function for this probability distribution is exactly given by this quantity. So it's like taking the trace of the density matrix, reduced density matrix with actual insertions of e to the I theta q sub A, where q sub A again measures the charge contained in A. Why do I say it's a generating function? It's because if you take the derivative of this quantity with respect to this U1 flux theta, you will be able to get, say, the average or variance and higher moments of the probability distribution. So in this way, this generating function, it gives you the data of the probability distribution to study the so-called full counting statistics of your symmetry charge distribution. Now I would like to say that here, again, you say like in this equilibrium setting, your in state and out state are the same. Then it's natural to think that what do we change for like dynamical processes and non-equilibrium processes? So again, you need to take care of the cross-term contributions. And this is exactly the n equals 1 generalized charge moment that I showed earlier. So basically, it's like taking the trace of this generalized density matrix where your in state and out state can be arbitrary with this actual insertion. So again, computing this is not very easy. But we were able to get explicit closed form analytical results for this n equals 1 generalized charge moment in this very compact boson theory. This gives us access to the symmetry charge distribution for one arbitrarily excited state or for this kind of dynamical evolution of probability distribution. And we are currently working on something to apply these formulas to study some quench processes involving Luttinger liquids because it's related to this compact boson CFT. Now, our results in our paper were mostly based on CFT techniques, but we also benchmark it with lattice simulations because otherwise, how do you know you get it right or not? In particular, we benchmark it against a calculation in the XX chain. So this gives you like one of the plots in our paper, which check the CFT result with this XX chain calculation after you do Jordan-Wigner to map it to for fermions. And we find a relatively good agreement. Okay, so that concludes part 1 of my talk. Are there any questions for this part? Do y'all get bored or like confused or anything? Okay. Okay, then I will go to part two. Okay, so part two has looks quite different from part one because now we're in this region. So it concerns the intersection between symmetries and defects. So in the context of topological defects. Now, as I said, like maybe a lot of people in Henry theory and maybe also in condensed matter, sorry, I don't want to discriminate anyone, have been thinking about this perhaps in the continuum, but today I would really like to focus on the lattice point of view. So maybe let me just say a few words on why do we care about these kind of things on the lattice. So I should say like it's very natural for condensed matter theories to start with a lattice, but for Henry theories, sometimes you prefer to have a continuum theory, field theory description. But I want to say that if you want to map between, say, your continuum theory and its lattice regularization, namely what kind of lattice theory flow to what kind of continuum theory in the infrared, this map is very complicated in general. So at the level of local operators, you know it's already complicated, even in the Ising model. Like then if you go to three-state pods, as if you didn't do much more on the lattice, but then this map becomes really, really complicated. And the same is true for extended operators. So now this topological defect, even though I just, draw this as a local modification, but it extends along time direction. So, there's maybe sometimes a dimensionality matching for Henry theory, D plus one, D is space, and for condensed matter, we sometimes don't include the time direct, but it is an extended operator. So the mapping between extended operators are even more complicated. However, if your defects is topological, that gives you extra constraints for you to pin down this map. So that gives you some extra mileage. But regardless, this is a crucial ingredient if you want to map your theories between continuum and lattice regularization. And of course, this gives you a new pathway for both analytical and numerical methods, and it offers you super setups for quantum simulation platforms. Okay, so although lots of things I'm going to say today could be generalized to other lattice models, and I will say I worked on some other lattice models as well. But today I'm just going to look at the sort of like a prototypical example of 1+1D quantum transverse field Ising model, which is given by this Hamiltonian, where in particular, you have the nearest neighbor interaction in terms of poly Z operators and transverse field in terms of poly X operators. A lot of what I'm going to say today could be translated into off-critical Ising model, but today for the convenience of the demonstration, I'll just set the system at the critical point. Now, there are exactly two topological defects in this transverse field Ising model. The first defect is what people call Z2 defect, but it's literally some sort of twisted boundary condition, if you wish. So instead of periodic boundary condition here, you would add some Z2 twisted boundary condition, which represents itself as just changing the sign of the poly-Z interaction at particularly this right bound. So effectively, you're applying your anti-periodic boundary condition. So the other topological defects is more non-trivial in the sense that you need to modify more things around this bound, but still it's all local modification. So in particular, you would modify this poly-Z interaction in terms of poly-Z, poly-X and delete the transverse field on this site. So this this is what people call Kramers-Warnir duality defect. It has been around for quite a while, and now recently there's a resurgence of interest in this subject for various different reasons. So there are people from mathematical communities who study fusion categories, and also non-invertible symmetries, and numerical people who study who use tensor networks, and where you could try to extract this sort of defect entropy or defect G function by doing some numerical simulation using this lattice Hamiltonian. And also there are people in from the community of quantum circuits, trying to implement Kramers-Warnir in some quantum circuits, or you study this kind of defect problem in some Floquet circuit setup. So there are many recent interests in this subject. But as I said, today I'm going to just focus on something that I think worth exploring, which is the relation or the roles played by topological defect in constructing these long-lived physical quantities. So why do we want to think about these long-lived physical quantities? We know that generic quantum systems are expected to thermalize where in the long time limit, your expectation values or local observables will reach some stationary values predicted by some statistical ensembles. And the information about the initial state of the system is typically lost. Now, of course, we know that integrable systems that don't symbolize in the traditional way, in the sense that you have this many conserved charges. So the stationary value, instead of predicted by a Gibbs ensemble, it's going to be predicted by a generalized Gibbs ensemble, taking into account these actual conserved quantities. However, you could argue that there are not so many natural integrable systems. So what could we say about more non-integrable systems? Whether you could find like many almost conserved quantities with long lifetimes. So in the literature, I should say like this kind of this kind of engineering problems where you try to find these long-lived quantities are not only have serious interest in like quantum many-body systems, but could also have practical implications in quantum information storage and processing. So traditionally, people have studied a lot two different setups. They have different flavors. So the first setup is the so-called weakly integrable system, which you could think of as being deformed from a particular integrable system. So the Hamiltonian is later written as an integrable Hamiltonian plus some deformation term. And this deformation term is engineered specifically. So it's not any V that would work. You should be able to find this kind of deformation such that you could also find these almost conserved charges, which almost commute with each other up to some corrections, which is quadratic in this deformation strength. So namely, in particular, this means that all charges commute with your Hamiltonian up to some corrections, which is quadratic in lambda. So in other words, you still almost have integrability. It's only broken at order lambda squared. So it's broken more weakly than a generic deformation, which would be order lambda. So this is what people call weakly integrable system. And a consequence of this almost conserving property is that these charges decay more slowly than predicted from Fermi's golden rule. And I will show you later some simple time model numerical analysis coming back to this point. And because you have these quasi-conserved charges, your total system will symbolize also slower than usual. So that's the first setup. The second setup has a different flavor with the first setup. Namely, in the second setup, these long-lived physical quantities have more to do with inhomogeneities of your system, namely boundaries or defects. So this question has been studied a lot for open boundaries, where people have engineered edge modes, the so-called strong zero modes or almost strong zero modes, where their lifetimes are much longer than the bulk symbolization time. Now, the relatively less studied are like what happens with topological defects. And this paper by Asimov and Findley was one of the first papers to say that topological defects can also enable isolated modes with long lifetimes. And with my collaborators, we also try to generalize this statement to periodically driven system instead of like ordinary Hamiltonian dynamics, but I will not talk about that today. So you have these two setups. This paper that I mentioned earlier with my collaborators sort of combine these two setups. So you have weakly integrable systems and you have systems with defects. What we do is to give the general framework to construct this kind of long-lived physical quantities for weakly integrable system, but enriched with defects. So in a sense, in this system, you have the benefits of both setup 1 and setup 2. In particular, there are two kinds of long-lived physical quantities. The first one is just these quasi-conserved charges, which is like extensively local, but they're modified by your defect. So you need to know how to modify these kind of charges. And the second quantity is that this defect also enables for you some localized modes with long lifetimes. So in this talk, I will just focus on this first part. The second part, I'm happy to tell you more about if you want to learn more about that. Okay, so I should say that although our this kind of procedure should be applied to any integrable systems with integrable defects, in this paper we use this example again of transverse field Ising model with a Kramers-Warnier duality defect using the fact that Kramers-Warnier duality defect is in particular integrable. And that's true for many other topological defects that you could use this, use this kind of setup. So let me first just tell you briefly how to engineer a weakly integrable system without any defects or boundary. So suppose I have a transverse field Ising model. I have the Hamiltonian written just as before. Now, transverse field Ising model is integrable. It has many other conserved charges. One of those is looks like this. So you have nearest neighbor poly Y, poly Z interaction, and you symmetrize it, anti-symmetrize it. Now, if you take this to this Hamiltonian and conserve charge and perform some sort of non-local operation on these two things, and this is something called a bilocal operation, which you could think of as some 1/2 of anti-commutator of your Hamiltonian Q, but with a prescribed ordering preference. So if you do that, you could generate for you a weakly deformed transverse field Ising model whose Hamiltonian looks like this. So this is your original Ising Hamiltonian. The deformation terms looks like this. So you have next nearest neighbor poly Z and nearest neighbor poly X. In particular, this deformation is self-dual on the Kramers-Warnier transformation. So this was studied many years ago by these people in the context of Mariana model after you do a Jordan-Wigner transformation, because this will give you 4 fermion interactions. Now I should say that in the continuum, this could also be useful for you because you could say like, okay, now I'm in the next nearest neighbor interaction. So it signals for you the deformation you turn on is irrelevant, but it's not any arbitrary garbage irrelevant deformation. In particular, this lattice Hamiltonian gives you a regularization for TT bar deformation of the critical, the Ising CFT. So in principle, people studying TT bar deformation would also be interested in this kind of lattice formulation. Okay, now what happens if I add a defect, say right here, like Kramers-Warnier defect right here, what changes? So this is what we worked out in this paper in October. So first of all, you have your defect modified Ising Hamiltonian, which has been known for 30 years, perhaps. But you also need to know how does your defect modify, this other conserved charge that I gave to you. So we work this out, and it just looks like this. So with some local terms, you just change to implement this defect. Now, the neat thing is if you just perform the same kind of non-local operation, this 1/2 of anti-commutator with the choice of this preference choice of the ordering, this will give you, a deformed Ising model with insertions of the Kramers-Warnier duality defect. So the Hamiltonian looks like this. You could say, okay, so what? How do you know this is even correct? It has lots of messy looking things. What we did in this paper is we derived the same kind of Hamiltonian using 2 completely different methods. So the first method is a so-called half-chain Kramers-Warnier transformation related to what people do in the non-invertible symmetry community by half-chain Z2 gauging. The second technique refers to like more mathematical community, which is you could use some techniques from Ising fusion category to derive this thing by modifying your projectors in the fusion category. So all these 3 methods, these 2 and the thing I just told you in the last slides, they look completely different, but they give you the same defect Hamiltonian. So this is a non-trivial check for all 3 of these methods. Now, of course, our aim is not to just get the Hamiltonian because, okay, what could you use? What could you do about it? So we also look into, quasi-conserved charges in this model and try to numerically verify their slower decay behavior. So to say that my numerical techniques are limited, that's also part of the reason I'm mostly in 1+1D now. But particularly for this kind of dynamical process, there are tensor networks, but it's the mileage you get from tensor networks is very limited if you want to study dynamical process instead of just focusing on low-lying states like ground states or first or second excited states. So what I do is just generalization at the moment. Okay, so you could work out, for example, the deformation you need to add to the original charge and looks like some complicated math. But then what one could do is to study, for example, the infinite temperature autocorrelation function of this charge. And if my deformation is generic, then from Fermi's golden rule, you would say that the early decay behavior should be controlled by your deformation strength lambda to the 2nd power. However, here, as you could see from this data collapse, where we're plotting infinite temperature correlation function against time multiplied with lambda3, you see perfect data points collapse at early times. And I should say that there's various plateaus here, which is related to the fact that we're considering a finite size system. So you would imagine if you have like 200 sites or like, and then you go to long times, they would all like, they would behave like a better, decay curve where you would observe like higher power dependence on this deformation coupling. Okay, so let me summarize. So I told you two stories. The first one is about entanglement, and second one is concerns topological defects. You could ask, what about this intersection between quantum entanglement and so it turns out there are also something interesting to think about. So for one, you could ask, how does the quantum entanglement depend on my defect? So it's not just like it's relevant to what kind of defect you insert, but also relevant where you put it. Conversely, you could ask the question, can I extract any physical information from quantum entanglement in presence of the defect? So in this paper, with another set of collaborators, we explored these kind of questions for the three-state Potts model, where we were able to extract defect entropy from non-entropy for some subregion in presence of defect, and also the defect G function. Okay, so that's all I have. Thank you. Yeah.
In the first part of the talk, you talked about so normal volume and entropy. You have it's more related to number of particles.
Yeah.
The number of particles here and how they're entangled.
Yeah.
In symmetry resolved entanglement, what you have these particles, which charge subset that they belong to.
Yeah.
So I'm just and can be cross term charge sector from one can also entangle with other. Is there any pattern like which like some charge sectors entangle more strongly than others?
Yeah. So in a sense, like you could like I showed you the setup where like the density matrix like block diagonal, but there are setups to like explore like there are off diagonal terms if you break the symmetry, like if you start with some states which is not a symmetry eigenstates. But I don't think there's a generic statement about which charge sectors are more strongly entangled. At least for the case I'm telling you today, it's just U1 symmetry. So like you say, each charge is like a dimension 1. So there's probably not something special there. But if you study non-abelian symmetry, I would imagine like representations with a higher dimension could be have a stronger effects in that. Yeah, please.
Is it possible that is there a possibility that you could have two charge sectors, subsectors?
Yeah.
They could never entangle with each other?
They could never entangle with each other. As long as you allow charge transport, I don't see why. That's yeah. Unless you physically just say don't interact with each other in some way. I think naturally. Yeah. As long as you allow charge transport without actual constraints, I would think that's perhaps not going to happen.
In some sense, what you realize if you have a total volume and entropy of A with a complement, you broke it into contributions coming from different.
Yeah, exactly. Yes.
And okay.
Yeah.
And the second part, this long-lived operators that you talk about.
Yeah.
Are there in some sense some kind of operator analog of scar when you go to scar?
Yeah, that's a natural question to do, but this is not many-body scars. So, yeah, that's this is not in some sense many-body scars. It's like it takes some engineering to give you these scar states, but here this the two setups I talk about. The second setup is like has to do with inhomogeneities in your system. So like you would have long-lived modes trapped at your defect or boundary, and that's quite different from the statement of many-body scar. And the first setup I talk about, weakly integrable system, it might have some relation with many-body scars because now there's a reason why there's a reason why your system will thermalize in a longer time scale. But I think at least I don't know the exact relation between weakly, like maybe people study Hilbert space fractionalization, like have something to connect these two, but I'm not an expert on that. Yeah.
Thank you.
Thanks.
I have
Yeah.
a basic question. You briefly mentioned about defect entropy,
Mhm.
but what is it actually measuring?
Yeah, so you could think of the following setup. So I have a 1D system. I put a subsystem, say like 5 sites in my spin chain, and I put a defect right in the middle of this subsystem. And then you could try to say what does a phenomenon entropy look like. So what as you could say, like you have some leading ordered behavior related to the subsystem size, but there's also some subleading term. So if you try to regularize everything carefully, you could extract this so-called defect entropy from the subleading term. So in some sense, in a more physical sense, regardless of entanglement entropy, this defect entropy or defect G function tells you the relative stability of the defect against local perturbations along the defect. So like think of like instead of turning on perturbations on my whole space, I'm just turning on some perturbations on the defect, and then there's some RG flow induced localized on the defect. When you say things like that, your buck is always in the critical point for setting this up. But then this G function sort of rank the position of your defect in this RG flow space. And then you could detect it using phenomenon entropy in the setup that I just told you about. Yeah.
Have you studied the relative entropy of this state with the defect and state without defect?
The relative, I don't do relative entropy. So what I do is more naive. So you literally just compute the entropy with defect versus entropy without the defect and subtract them.
Right.
It turns out when you subtract them, all your lattice regularization data and such will cancel out, and then what you get is log of the G function or defect entropy. So
Right.
that's a very special case. It only works in 1+1D. So you could think of like, what about higher dimensions? There's some tricky thing there. So like in 2+1D, I could also put a line, put a impurity somewhere, and then in the middle of say some subregion like circle. No, the pi like sorry. The subregion like that, and then you could ask like whether the subleading term later gave you defect entropy. There's some actual data you need to consider. So basically, your box stress tensor 1-point function coefficient also plays into there. So it's a subtle relation in higher dimension, but in 1+1D, you could reliable extract defect G function just from the subleading term that I told you about. Yeah, thanks.
There's a question from the online chat. Could you comment on the presence of online page states that are enabled by defects you mentioned by passing?
Could I comment on the presence? Yeah. So, let me try to. I forgot which one so it works. Sorry, just one moment. So, I didn't talk. Okay, I didn't talk more about here, but basically what happens here is a special case where that's why I said enable. So in a sense, your existence, your topological defects in this sense, in this case, Kramers-Warnier duality defect somehow enables for you to have some isolated zero modes that if you the set I'm considering here, everything's at the critical point, but that's not the setup for this. Just considering the following setup, I have a circular chain, and I'm putting Ising model in 2 phases. Ferromagnetic phase on say 1/2 of the chain, and paramagnetic phase on the other half of the chain. Or like doesn't have to be half, just one part, the other part. And then what do you put at the boundary of these 2 phases? At the first boundary, I'm inserting a so-called Kramers-Warnier duality interface. It's literally just like what I told you earlier, except now it's an interface between the 2 phases. And then at the other half, I'm putting a domain wall in coupling space, which takes you between the ferro and paramagnetic phases of the Ising model. And what you realize is like if you do Jordan-Wigner transformation, this model is exactly solvable. And in particular, in each of this Z2 charge, so Ising has a Z2 charge, and in each Z2 charge sectors, you will find a trapped zero mode trapped as a domain wall. Now, of course, you could say this is a domain wall that seems to have nothing to do with Kramers-Warnier interface. That's not true because there's some tricky non-local thing you need to do when you Jordan-Wigner. I didn't put stats in here, but basically the statement that when you insert smart duality interface that allows you to have like an odd number of domain walls in this circular chain business, then you could trap, isolated zero modes at the domain. And if you do this limit where you shrink one of the face to zero size, then this zero modes will be trapped as a duality defect. So that's like the general story there. This paper sort of worked out the story for like a Hamiltonian dynamic. The setup described by Hamiltonian, and you could show that in Floquet circuits, which is like this periodically driven system, you could always also find these isolated modes which get trapped at the domain wall or when you shrink one of the faces to zero size at the defect. So I feel like maybe I should have talked into the computer, but is that helpful for the online person? Okay.
Hey, any other questions?
Yeah, can I?
Yeah.
Sorry, just
No, that's fine.
be clear that I understood correctly.
Yeah.
When you have different charge subsectors, is there any discrimination or any constraints on how they entangle with each other?
Is there any discrimination? Like I said, if I'm considering non-abelian symmetry, this probably has some relation between like dimensional representation and stuff. But for you, I don't think so. Because there's no yeah.
So the dimension of the representation, it will probably reflect in the set also, right? That more particles carry this kind of.
Yeah, that's why I will.
So
Yeah, but I don't know. I don't have a.
Okay.
Yeah, the short answer is I don't know, and I imagine in non-abelian symmetry there will be discrimination depending on your group theoretical meaning of your representations, like dimensional representation and things like that. For U1, I don't expect to be. Yeah. Thanks.
Okay, so if no question, let's thank the speaker again.
All right. Thank you.